Welcome. The instrument cluster of a vehicle provides the driver with a lot of information on how the vehicle and vehicle systems are operating. From the gauges and warning lamps that provide critical information on vehicle speed, and engine temperature, to fuel gauges, brake system warning lamps, and malfunction indicator lamps for the engine control, anti-lock brake, supplemental restraint airbag systems. In this video, we'll look at how these gauges and warning lamps work and how to diagnose electrical problems in the instrument cluster. After viewing this video, you should be able to inspect and test gauges and warning lamps, inspect and test sending units, inspect and test printed circuits, diagnose the cause of incorrect gauge and warning lamp operation, and inspect and test sensors for electronic gauges. There are two types of analog or non-electronic gauges commonly used on passenger vehicles. The first is the magnetic gauge. A magnetic gauge, sometimes called a D'Arsonval gauge, uses a magnetic field to move the needle on the gauge. In a D'Arsonval gauge, a coil of wire is wrapped around the base of the pointer needle to form an armature. When current flows through the coil of wire, a magnetic field is created in the armature. That field is opposed to a permanent magnet that surrounds the area of the needle. The needle of the gauge moves in response to the strength of the current that flows through the coil. This type of gauge is commonly used as an ammeter on the instrument cluster. A variation on this type of gauge is the bobbin gauge. A bobbin-type gauge uses a bobbin assembly to create the magnetic field that causes movement of a shaft to which the indicating needle is attached. A common bobbin-type gauge is a temperature or fuel level gauge. The second type of gauge is a thermal gauge. The thermal gauge is also known as a bimetallic gauge that operates when a controlled current flows through a heating coil. The heat causes the bimetallic strip to bend in proportion to the heat of the current flow and the needle moves. A common type of bimetallic or thermal gauge is the fuel gauge. Many analog gauges require the use of an instrument voltage regulator to maintain a constant voltage to the gauges under all electrical load conditions. These voltage regulators use a bimetallic arm and heating coil to open or close a set of contacts. While the operating voltage of gauges varies with manufacturer, typically the regulators will limit voltage to up to 10 volts. When voltage through the regulator exceeds 10 volts, the bimetallic strip expands and opens the contacts. As the strip cools, the contacts are closed and voltage is again allowed to the gauges. The continual opening and closing of the contacts regulates the voltage. Where a separate voltage regulator is not used, the voltage regulator function is built into the gauge. In order for a gauge to work, there must be a sending unit. The sending unit provides information to the gauge in the form of a voltage signal. The function of the sending units for the gauges, such as the engine temperature and fuel level gauges, is to vary the voltage signal to the gauge in response to the varying conditions. These types of sending units are appropriately named variable resistors. A fuel level sending unit alters the voltage to the fuel level gauge in response to the position of a float in the fuel tank. The float is connected to an arm that sweeps across a scale that has a progressive resistance. At one end of the scale, there is very high resistance to current flow. The other end of the sweep scale has a very low resistance. As the position of the sweep needle, controlled by the position of the float in the tank, changes, there is more or less resistance to the flow of current through the sending unit to the gauge. The resistance in a fuel level gauge increases as fuel level decreases. The change in resistance as the float drops causes a lower current flow to the gauge. As a result, the magnetic field of a magnetic gauge is reduced, causing the needle to drop. On a thermal gauge, the bimetallic arm is cooled, causing the fuel needle to drop. The coolant temperature gauges work off of the signal from a sending unit called a thermistor. A thermistor is a sending unit that varies resistance in response to temperature. Thermistors can be either positive coefficient thermistors, meaning that their resistance increases as the coolant temperature increases, or negative coefficient thermistors, meaning that their resistance decreases as temperature increases. The engine temperature gauges are designed to work in conjunction with the type of sending unit used. On a negative coefficient temperature sensor, there is high resistance when the engine is cold. This results in the gauge needle moving very little in response to the decreased current flow through the thermistor. As coolant temperature increases, more current is allowed to flow through the circuit, resulting in a greater movement of the temperature needle. Warning lamps are often used either in place of or in addition to gauges on the instrument panel. Warning lamps are either on or off, depending on the condition they're monitoring. Common instrument panel warning lamps include a brake warning lamp, a low fuel lamp, an oil pressure lamp, and a seatbelt warning lamp, among others. In addition to these types of lamps, there are several malfunction indicator lamps that respond to signals from electronic control units that monitor the engine, transmission, and supplemental restraint systems. The lamps that are not electronically activated through control units all use some form of switch to open or close a circuit to ground to turn the lamp on or off. A typical example of a normally open switch is the oil pressure switch for the oil pressure warning lamp. The oil pressure sending unit uses a diaphragm that moves up or down in relation to oil pressure. When oil pressure is in the acceptable range, the contacts in the sending unit are separated and the circuit is open. The lamp is not illuminated. When the oil pressure drops below the acceptable level, a set of contacts in the switch are closed and the circuit to ground is completed. The lamp is turned on. Another example of a normally open switch is the brake fluid switch. On this switch, the contacts are normally open and the lamp is off. A float in the brake fluid reservoir will drop with the level of the fluid in the reservoir. When it drops too low, it closes the contacts and the brake warning lamp illuminates. Another variation is the coolant temperature sender for a temperature light. On this normally open switch, there is a bimetallic arm that moves as it is heated. When the coolant temperature rises to an unsafe level, the bimetallic strip expands and the switch contacts close, completing the circuit to ground that causes the temperature lamp to light. A normally closed switch is the seatbelt warning lamp switch. On this type of switch, the warning lamp remains on until the buckle is inserted into the latch. Inserting the buckle separates the switch contacts and the circuit is opened. The lamp goes out as a result. With malfunction indicator lamps, the bulb circuit is operated by the electronic control unit to illuminate the lamp. When a problem is detected in a monitored circuit of a system, the control unit closes the circuit for the lamp and the lamp illuminates. Under some circumstances, the electronic control unit will continually open and close the lamp circuit to cause the lamp to flash a warning to the driver. As you can see, there are many variations on the types of switches used for warning lamps, but the principles remain the same. When the circuit to ground is completed, the lamps illuminate. And when the circuit to ground is opened, the lamps are extinguished. Most of the speedometers on today's vehicles are electronic speedometers. An electronic speedometer uses a sensor on the transmission output shaft to generate an analog signal that is sent to the speedometer on the instrument panel. The sensor is known as a vehicle speed sensor. The vehicle speed sensor has a magnet in the sensor. A toothed wheel on the transmission output shaft rotates at the same speed as the shaft. A tooth of the wheel is a conductor that passes by the magnet in the sensor. As the conductor passes the magnetic field, a voltage is induced in the wire to the speedometer. When the tooth passes by the magnet, the voltage is no longer generated. The faster the shaft of the transmission turns, the greater the frequency or cycles per second of the signal from the vehicle speed sensor. An electronic speedometer has a signal converter that changes the analog signal to a digital signal. The result is a speedometer needle that is moved in response to the frequency of the signal from the speed sensor. Tachometers are used to display the engine speed in revolutions per minute. A tachometer operates in a manner similar to the vehicle speedometer, using a toothed wheel on the engine crankshaft to send a signal to the vehicle's powertrain control module. The sending unit for the tachometer can either be a magnetic signal generating sensor like the vehicle speed sensor, or a Hall effect sensor that generates a signal when a semiconductor layer is exposed to a magnetic field. Or it can be a photoelectric sensor that generates a voltage signal as light is passed through a cutout in a wheel that is located inside the distributor and rotates with the distributor shaft. The magnetic sensors are called variable reluctant sensors, and the toothed wheel on the crankshaft is called a reluctor armature. The teeth on the reluctor armature are equally spaced around the wheel. There is one tooth missing that indicates the position of the number 1 cylinder piston at top dead center on the compression stroke. The analog signal generated by the crankshaft position sensor is sent to the powertrain control module, also known as a PCM. This signal is converted by the PCM to a digital signal, where it is used as one of the inputs for calculations of fuel and ignition timing. The signal is processed by the PCM, and an output signal is sent to the electronic tachometer, where it is displayed for the driver's information. Some of the newer vehicles feature a driver's information module. The trip computer display provides the driver with a clock and a display of distance to empty calculations, average vehicle speed, driving time, and an outside temperature. A mode button on the trip computer is used to cycle through to the desired display to access functions. The distance to empty or DTE function uses inputs from the vehicle speed sensor or VSS, tachometer, injector pulse signal, and the fuel level sensor to calculate fuel consumption and provide the driver with the distance that can be driven with the available fuel. Fail-safe capability is incorporated into the distance to empty function. A vehicle speed sensor, tachometer, or fuel level sensor signal failure will cause the display to be fixed at its present value. Failure of the injector circuit will cause the trip computer to perform a fixed calculation of the distance to empty. In the event of a fuel injector circuit failure, the trip computer will show a steadily declining distance to empty based on a programmed calculation. The average vehicle speed is computed by taking the driving distance from the vehicle speed sensor signal and dividing it by the driving time. A loss of the VSS signal will cause the display to be held at the current value. The driving time and clock functions are self-contained within the trip computer, and with the exception of battery power, do not require external sensor input. The ambient temperature function receives input from a temperature sensor located at the front of the vehicle. Most customer concerns related to gauges will fall into two categories: gauges that don't work and gauges that work improperly. Always begin your diagnosis of a gauge problem by confirming that the condition exists. Then develop a diagnostic strategy to determine the cause of the problem. This strategy should start with a review of the wiring diagram and the system operation found in the repair manual. An inoperative gauge is usually related to a circuit problem, while a gauge that operates improperly is usually an indication of a problem with a sending unit or excessive resistance in the circuit. Now let's take a look at some examples of how you might approach both types of problems. The owner of this vehicle complains that the fuel gauge doesn't work. Let's start by confirming the complaint. With the ignition key in the on position, the gauge needle doesn't move. The owner said they just filled the tank with fuel, so we know it has gas in the tank. So let's continue. The wiring diagram shows that the fuel gauge gets power from the gauge fuse in the fuse panel. That fuse supplies power to all the gauges, and the other gauges work, so we can eliminate that as the cause of the problem. We can tell from the wiring diagram and our understanding of sending units that the fuel tank sending unit controls the ground side of the circuit on this vehicle. That means current flows through the gauge to the sending unit and then to ground. The sending unit varies the resistance in the circuit that alters current flow through the gauge and causes the reading on the gauge to change. We also know that as fuel level decreases, the resistance of the sending unit increases. So if the gauge is reading empty, there must be high resistance in either the sending unit or the circuit to ground. Let's test the sending unit with an ohm meter to see if it's working properly. On older vehicles, it was possible to use a jumper wire to ground the sending unit lead to the gauge to check the gauge. Because of the gauge design and the interrelation of systems on today's vehicles, this is no longer a valid test, so don't use that approach. To test the sending unit, disconnect the connectors and remove the sending unit from the tank. Then connect a digital multimeter set to the ohms test to the sending unit. If the sending unit is open-circuited, meaning it always has a high resistance, the meter will display OL for over limits. We have a reading on this sending unit, so let's check it through the entire range of operation by moving the float. The readings on the meter display decrease as we move the float arm upward. We can see that the sending unit varies resistance through the range of the scale, so it looks like our sending unit is okay. The wiring diagram shows us that the last point to check is the ground for the sending unit, so let's look at that. We can test the continuity of the ground with the ohm meter. Touch one probe to the terminal end and the other to a chassis ground. There should be a reading of 0 ohms if we have continuity. Our meter shows OL, or over limits, meaning we don't have a complete circuit. No wonder the gauge doesn't work. Let's take a look at another example of a gauge problem, a gauge that is inaccurate. The owner of this vehicle says that the engine temperature gauge doesn't move more than 1/4 of the way up from cold, no matter how long the car is driven. They said the gauge used to go to almost halfway when the engine was warm. Let's start by checking the car. Just as the owner said, the gauge moves from cold and stops about 1/4 of the way. Let's look in the repair manual to see how the system works. The manual says the sending unit for the gauge is a negative coefficient thermistor, which means that the resistance of the sensor should drop as the engine warms up. The repair manual also tells us that an engine that doesn't warm up to operating temperature might have a thermostat that is stuck open, or a cooling fan that is operating all the time. Let's check those out while the car is warm. If we feel the upper radiator hose, we can feel coolant flowing through the hose to the radiator. We might have a bad thermostat. We can check the radiator fan visually. The electric fan is off, so that's not the cause. Let's use a digital pyrometer to check the temperature of the coolant returning from the engine through the upper radiator hose. It seems like the temperature is in the normal operating range, so we can eliminate the thermostat as the cause of our problem and go to the gauge circuit. While we wait for the engine to cool down, let's take a look at the wiring diagram. The circuit for the temperature gauge shows that the gauge gets power from the gauge fuse. Since the gauge works, we can make sure the power side of the circuit is okay by checking the voltage at the sending unit. On this car, the voltage to the sensor should be battery voltage. Okay, we have nearly 12 volts at the sensor. The problem must be with the sensor or on the ground side of the circuit. Okay, the engine is cooled down, so let's test the sensor. The chart in the repair manual tells us that we should have about 2 kiloohms at 70 degrees engine coolant temperature. Let's use a thermometer to see what the temperature of our coolant is. The thermometer shows 100 degrees, so using the chart, our resistance should be between 1 and 2 kiloohms. Our reading is in that range, so let's check it further. Remember that an ohm meter can't be used on a live circuit, so we can't run the engine and watch the resistance change or we'll damage the meter. But we do know Ohm's law, and Ohm's law tells us that as resistance increases, voltage decreases. And we can use a voltmeter on a live circuit, so let's change the meter to test voltage. Our repair manual tells us that the voltage out of the sensor at our coolant temperature should be about 2 volts, and that the voltage should drop down to about 1 volt when the engine is warm. Let's watch and see. The voltage is dropping. Wait, it stopped at about 1.5 volts, and it's staying there. Let's see where the gauge is, just where the customer says it stops. Let's change the sensor and see what happens. Looks like the sensor was the cause of our problem. You can see how, with an understanding of electrical principles, wiring diagrams, and a sound diagnostic strategy, we can narrow down the causes of gauge and lamp problems quickly and easily. In this video, we've looked at the gauges and warning lamps that provide information to the driver, how they work, and how to troubleshoot problems when they do occur. Thanks for watching.